Right, so we're going to finish up chapter 1 with lesson 1.9, Introduction to Parent Functions. So this is actually, there's a chart of some of the parent functions here. And if you look over on the board over there, there's actually a poster that says parent function that tells all of them. And one thing I don't have on here is a pointer, so I've decided that Mr. Smiley Face is my pointer. So the one thing is, like I said, that the only time you ever see anything happening there is if I'm actually moving something around. So when I'm talking, you don't see it. So I'm going to use the smiley face as my pointer to point at things. So here we're talking about parent functions. Well, we've all seen all of these different things, and here's the list of them. There's the constant function, where all that is just a horizontal line. Could be y equals, or f of x equals 5, 7, negative 8, whatever. Then the parent function for a linear is just a line y equals x. Okay, we've all seen that line. And the quadratic parent function is x squared. Okay, everybody knows what that looks like, the quadratic. And the cubic function, x cubed, and the square root. So these are all the parent functions. They're the most basic of all of them. Now for all of those, you can add 5 to them. You could divide by 3. You can multiply by 7. Okay? But the main thing is that what the parent function is. And one thing you'll notice is that we talk about a lot of different things here. So we've got what the function is, the rule, what the graph looks like. And the graph of these, no matter what I do to them, is going to have that basic shape. Right? The only difference here would be the cubic function. Sometimes that looks a little bit different when I add different stuff to that. But the basic shape is going to be the same. Okay. Square root function. Right? That one's the one that you haven't seen very much of. Here's the domain, which when we're talking about domain, what are we talking about? Okay, the values of x. All right, you notice for constant, linear, quadratic, and cubic, it's all real numbers. But for the square root function, it says it's greater than or equal to 0. Why? Why does the value of x here have to be, why does it have to be greater than or equal to 0? You can't take the square root of negative. That's right, Jacob. All right, and the range. Okay. So y equals c, it's always going to be for the constant, just going to be whatever that number is. For linear and cubic, it's all real numbers. For quadratic and square root, it's y is greater than or equal to 0. Okay. Now, these are, any of them that are, the degree is odd, okay? Like the degree of the linear is 1, the degree of the cubic is 3. Any of them that are that, the domain is always going to be all real numbers. Or the range is going to be all real numbers. For the even function ones, like quadratic, okay, for instance, it's going to be y is greater than or equal to some number, or it could be less than or equal to some number. And notice the other thing about all of them, they all intersect the origin, except for the constant, right, at 0, 0. Here, give you a little helpful hint about graphing. For accurate graphs, use the standard square window. So hit zoom 6 and then hit zoom 5 to make it fit. All right, so here we go. Identifying a parent. So for letter A, they want us to identify the transformations of parent functions. So we want to identify the parent function for G from its function rule, then graph it on our calculator and describe what transformation does it represent. So x minus 3. So first of all, what's the parent function here? If it just says x minus 3, what would that parent function be? So which one of these 5 is it? And the way to look at it is look at the power. Okay? This has x, right? Okay? There's no power to that x, so it is linear. Okay? So this is going to be a linear function. That's the parent function. All right, so go ahead and graph it, and because we want to tell what the transformation is. So put x, and what you can do to help do this is graph both of them. Graph the parent function, first of all, x, and then graph x minus 3. So the first one you graph will be the parent function. The second would be the, oops, and what did I not do?
You didn't fix
The window, right? Zoom 6. So what's the transformation here? Okay. Linear is the parent function, so what did it do? Carolyn, what did it do?
down.
It moved down 3. Okay. So this is a vertical shift down 3. Did anybody think it might be to the right 3? In this case, actually, you could have said either one and would have been correct as far as this parent function. But because the 3 is out here, okay, then I would have said it's down 3. Okay, just like that. All right, letter B. Brandon, which parent function is this one going to be? Okay, look at the power. Look, it says x squared, right? Okay, I'm always looking for the power. So which one of these has a power of 2? Quadratic. Okay, so there you go. Our parent function is quadratic. And then what would be the transformation? If we look at the graph, here's the parent function, and here's our function of x squared plus 5. What's the transformation here? Brittany? Up 5, yep. Okay, so this is going to be a vertical translation, up 5. So you're just identifying which parent function it is and telling which way it moves, left, right, up, or down. Okay? Okay. It's often necessary to work with a set of data points. So sometimes we actually have to make graphs and do it from there. So we're going to identify parent functions by having a table of values and do it. So we're actually going to have, you're going to actually do a little bit of graphing too. And I didn't get out the graph paper yet, so we'll have to do that. So let's go ahead and grab yourself a sheet of graph paper. Or the first person in each row grab graph paper for you. Okay, so we're going to identify parent functions from a set of data. All right, so here we have in, you don't have to do this, I'm making the table because I want to be able to see what the transformation is also. So you might want to make a table also. Yes, John? Okay.
I thought 2x values with the same output, it wasn't a function.
No. If, as long as the x values are different, it's a function.
Oh, all right.
You're looking for the same x value. Nope, the y values doesn't matter. All right, so we're going to go ahead and I'm going to put in these points here. Yeah. All right, so we got -2, and I'm going to make it. I'm making a table because I want to be able to see the transformation. So you see, I only have 2 parts of the table here. All right, but I'm going to add a part to that table also. All right, so I got -2 and 12. Oops. And -1, 3, and 0, 0. 1, 3, and 2, 12. All right. And I'm going to graph that. Oops. I want that. My graph's not big enough, is it? All right, so let's see. Let's pull this down here. And, okay. And so, come on, be my friend today. There we go. All right, so there's my points. What's the parent function there? Quadratic. Okay, so it's definitely quadratic. Can you tell what the transformation is? Well, that looks exactly like the quadratic. All right. Now I want you to graph on your calculator y equals x squared. Okay. And go to the table. And I'm actually going to add some lines here. And I'm going to put in the parent function x squared. All right. So if x is 0, what's 0 squared? 0. Okay, all right. So that point's still going to be there. Okay. If negative 1 is squared, what do I get? 1. Okay, so I have the point negative 1, 1. All right, that'll be right there. And if I square negative 2, I get 4. Okay, so that's negative 2 and 4. All right. And if I square 1, I get 1. Okay, so that's there. And if I square 2, we get 4. Okay, right? So, how do these y values for this set of data compare to the y values for our parent function? So how does 12 compare to 4? Well, go the other way, though. We want to go, what do I have to do to x squared to get multiplied by 3? Which means that I have a transformation that is 3 times bigger. Okay, so we have a, what do we call that when we're talking about transformations then? If I'm making the numbers 3 times bigger, that means I'm stretching it. Which direction?
Down.
Up would be horizontal, right?
Down.
Or vertical, right? Okay, so this would be a vertical stretch by a factor of 3. Which means that this then is y equals 3x squared. Let's see if it still likes me today. There we go. Oh, there it is. So we have a quadratic that is vertically stretched by a factor of 3. And so all I have to do is multiply x squared by 3. Okay, so here is another set of data. All right, so you determine what the parent function is and what the transformation is. And I'm going to pause. Now, so we're going to consider 2 data points, 0, 0, and 1, 1. They're on all of them. So if you plot them on a coordinate plane, you might very well think that they're a part of a linear function. In fact, they belong to all of them. So you have to be careful about those 2 points. Remember that any parent function you use to approximate a set of data should never be considered exact. Okay? It's going to be approximation. However, these approximations are often useful for estimating unknown values. You know, when they're doing sales, people that do sales, they're always thinking about, okay, you know, what's the best model that's going to fit it? Or They're doing different kinds of projections for their company. They're always looking at those things. So we want to graph the relationship from year to sales in millions of dollars and identify which parent function best describes it. Then use the graph to estimate when cumulative sales reach $10 million. So here's a great example. Look at this. This says sales in millions of dollars. So when I put these numbers on a graph, are they going to be very far apart? No. But when reality, this is $1.2 million apart. Okay? That's a lot of money, really. I mean, when we look at it. But when I put that on a graph, I can make it look like that's almost nothing. So it just depends on your perspective. All right. So we're going to make a graph. And so let's do this together. We're going to start out and use our wizard. So which kind of graph do we want for this?
A quadrant.
Okay, we want a quadrant graph, all right? So we'll pick a quadrant graph. All right. All right. Now, what do we want for our x values? X is going to be what? Years, okay? And so for years, we want to go 1 through 5, okay? So we'll start at 0 and we'll end at, we should probably go a little bit past 5, right? So we'll say 7. Okay, and what about our y values then?
Sales.
Okay, that's our sales, and we want to go where? 0 to where? Okay, maybe 15, because if we go to 15, we can go by 3s then, right? We could if we wanted to, right? So let's go 0 to 15. Oops, gotta go up. And we could go by 3s. Okay, and finish. It's up here. I want that. I want this. There we go. All right. Oops, I went by 5s instead of 3s. I'll fix that. Properties. 3. There we go. Okay. All right, so let's plot those points. And so it says identify which parent function best describes it, then use a graph. All right, so we'll plot the points here. And we've got 1 and 0.6, so that's probably about here. And 2 and 1.8, that's about halfway to 3, so about there. 3 and 4.2, so that's probably about here. And 4 and 7.8, so 4 to 7.8, that's about halfway in between there. And 5 and 12.6, that's probably about here. Okay, so which one do you think that is? Okay, it curves a little bit. All right, so let's see if I just made a dotted line here to connect these. All right, it looks like this. Okay, so which one is that? Okay, it looks like it'd be quadratic. It looks like it could be cubic. Do I know which one it is? No, I don't right at the moment. But did we study a situation where I could figure that out? Where we did differences? First differences and second differences? Like that? Okay. All right, so we actually could find it out. So, but it looks like to us, this probably looks like a quadratic, right? All right, so we can say it's a quadratic. So our parent function is a quadratic. Okay. And it says, then use the graph to estimate when cumulative sales reaches 10 million. All right, so 10 million would be about here, right? All right, so 10 million in sales would be there. And then if I came down here then to my x value, it's, what would we say that is about?
4.5.
Okay, so it would be $10 million. So, all right, in 4.5 years, it will reach $10 million. Okay. So it's just a matter of drawing, making a rough sketch of a graph. Okay. And then from that rough sketch of the graph, then we figure out what kind of a function does it look like. And then from there, we will go ahead and graph it and find the answer to the other part then.